You should understand the concept of what we are talking through the virtual laboratory, and also uh, there are some questions you have to solve that, and that is for the concept clearance. Okay. So very good morning to all of you. Myself, Professor Moodys Mirza from Maulana Mukhtar and Technical Campus, Mansoura Malegaon. This is our 30th lecture for FM fluid mechanics. Today is 24th of December 2021. Okay. So today, in previous class, we have seen the velocity distribution uh, by using the Prandtl's mixing ring theory, and today we will see Today we will see the frictional losses in pipe flow problem. So it is also called as energy losses in pipe flow, energy losses in pipe flow, because in this unit we are studying the pipe flow problem. Okay, so it is energy losses in pipe flow, you can say, and these losses, it may be the major loss and minor losses are there. Okay, in the pipe flow problem, and also we will see the reasons of that losses. In minor losses, there are many losses are there. In major losses, you can say that friction loss is the major loss, and in minor losses, there are number of losses. You can say it may be uh, sudden construction of pipe, sudden contraction of pipe, sudden expansion of pipe, expansion of pipe at the entry. There is sudden loss at the exit of the discharge. The exit of the discharge, there is some losses. Entry and exit. These minor losses we will see. So we will start with the major loss, that is the frictional loss in a pipe flow. In a pipe flow. So when a liquid flowing through a pipe, the velocity of liquid layer adjacent to the pipe wall is zero. So this is your pipe wall. What we are considering, at the near the pipe wall, the velocity is zero, and this is the velocity gradient. Yeah. Because it is moving in the air. So at the center, the maximum velocity will be there, and as it proceeds towards the wall, the velocity is reducing. The velocity is uh, reducing. Okay. So this is so at the wall, the velocity we are considering zero, and the velocity of liquid goes on increasing from the wall, and thus velocity gradient also increases, and hence shear stresses are produced. Shear stresses produced between the two layers of moving layers. Uh, in whole liquid due to the viscosity, and that shear stress is developed due to the viscosity, and this viscous action causes loss of energy, which is usually known as frictional losses. So in the pipe flow problem, The frictional losses are the major loss. So William Fraud, on the basis of experiment done by him, he suggested uh, some of the frictional losses in the turbulent flow and given the following losses of the fluid friction for the turbulent flow. And the frictional resistance for turbulent flow, it may be uh, proportional to, it may be proportional to so frictional losses in pipe flow for turbulent flow, for turbulent flow, it may be due to or proportional uh, proportional to v to the power n, where n varies from 1.5 to 2. Okay. Also, the proportional to the density of the fluid is also proportional to the, sorry, I read on, it is proportional to the proportional to proportional to proportional to density of fluid, density of density of fluid. So fluid density also affects the movement between the layers, and that's why the frictional losses are there. It is also proportional to area of surface area of surface in contact, area of surface in contact, and it is independent of it is independent of pressure. It is not dependent on the pressure. The frictional losses, they are called the major losses in case of pipe flow problem, and it is also depend on nature of nature of surface in contact, इन कॉन्टैक्ट स्मूथ सरफेस है तो कम फ्रिक्शन रहेगा और रफ सरफेस है तो ज्यादा फ्रिक्शन रहेगा. So before going for that, for the losses for the resist frictional factor, we will see the Darcy Weisbach equation for loss of head in pipe. So before going that, for the friction factor, we will see the Darcy Weisbach equation for loss of head in a pipe. Loss of head in a pipe. Okay. So we will draw a pipe. This is your pipe. The discharge is Q. Okay. This is the pipe. Okay. Fluid is flowing from the pipe. The fluid flowing through the pipe, having some velocity. The diameter of pipe we consider a D, and we consider a two section in the pipe network, section 1 and section 2. Section 2. And the difference between the two sections, we said that is length L. The pressure here will be, if I will say the pressure here will be P1 and pressure at the section 2 is P2 and resistance to the motion is, that is shear stress. At the boundary, at the wall, it is velocity is 0, that's why tau 0. Okay, so that's why this figure, I will say this figure number 1, flow through the circular pipe. Okay, so we will come to the head loss between these two sections for the Darcy Weisbach equation for loss of head. So flow through pipe is characterized as a pressure flow, as the flow is taking place at expense of pressure energy and it is opposed by frictional resistance at the pipe pole. Thus, if P1 is and P2 are the intensity of pressure at section 1 and P2. So if I will say that P1 is the intensity of pressure at section 1 and P2 is intensity of pressure at section 2 and section 2. We have to write whole, at section 2. So difference in the pressure, if you will, and L is the distance between section 1 and section 2. Okay, so if you write down the pressure difference, that's P1 minus P2 depend on the cross section area is equal to the friction resistance is due to shear stress and it is pi d, the perimeter of pipe, and we are considering into only a small portion of the pipe, that is length L. That's length is L. Okay, if I write down in terms of pressure only, so it will be tau 0 upon A into pi dl. Okay. So if you putting gamma into HF is equal to tau 0 pi d upon A into L. This is the pressure difference between the two. Okay, and HF is the head loss. So if I write down the pi into D is nothing but it is weighted perimeter. Weighted perimeter at surface of the pipe, you can say, because diameter is D, weighted perimeter, and that is denoted by P. And A is the cross-section area of your pipe. Cross-section area of the pipe where the liquid is flowing. Okay, so this figure is very important. Based on that, we are finding all of these things. Now you know that, because you know that P1 minus P2 is nothing but gamma into HF. Okay? So that's why we have come to that other formula. Now you know that tau 0 is equal to rho F upon 8 into V square. This is from as per in unit number 3 we have solved this as per Reynolds experiment findings for turbulent flow in a pipeline. Okay. Hence, here this F is the friction factor. F is here friction factor. So if you write down what will be the HF is equal to rho F into gamma 8 into V square into pi dl upon area is pi by 4 into d square, area of pipe. This is nothing but your area of pipe. Okay? And you know that this is rho into G, gamma is rho into G. So HF will be, write down, F L V square upon this 4 will come here up, so 4 it will come 2 into G, rho will cancel into D square into D cancel, 1D will be cancelled, only 1D will be 2 rho into G, 2 GD. So this is the thing, but your HF value, that is head loss as per the Darcy Weisbach equation. This equation is here nothing but Darcy Weisbach equation for the head loss. So HF is head loss, and here F is the friction factor. F is the friction factor. Or if F is the friction factor, or if F dash is expressed as a friction coefficient, if F is expressed as a friction coefficient, F dash, so it will be given that F, the friction factor is 4 times of F dash, that is friction coefficient, 4 times of friction coefficient. So if I will write down, HF will be is equal to 4F dash LV square 4F dash LV square upon D into 2G or 2GB. So this equation can be again written as, HF is equal to FLV square upon D into 2G, where F is the where F is friction factor, friction factor, and F dash is friction coefficient, and where F dash is the friction coefficient and is nothing but F divided by 4, or point or 0.2 pi into F. You can write out 0.2 pi into F. This is the friction factor and friction coefficient. Now the values of friction factor for different range of your Reynolds number. I will write down values of friction factor for different ranges of Reynolds number. And Reynolds number is here denoted by capital R. Okay. So first, the suggestion by the scientist is for laminar flow, friction factor is F is equal to 64 divided by R, and this is for R value less than equal to 2000, and R value less than equal to 2000 is nothing but the laminar flow. So substituting this value in equation, that is Darcy Weisbach equation, of head loss. So you can write down, it will be HF is equal to 64 by R, this value of F, LV square upon D into 2G. So if you write down this, 64 LV square divided by RD into 2. So it depends on the Reynolds number. And if you find out the R, you know the Reynolds number R is nothing but rho Vd upon mu. Rho is the density, V is the velocity, D is the diameter, mu is the dynamic viscosity of your fluid. So HF you can write down, HF 64 LV square, ये म्यू आर ये नीचे रहेगा तो ये म्यू ऊपर आ जाएगा, म्यू, और आर की वैल्यू क्या है, रो वी डी 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 स्क्वायर हो जाएगा 2G, ये 2 से ये 64 कैंसिल हो जाएगा तो क्या आ जाएगा यहाँ पर ऊपर, इट विल बी 32 म्यू LV square upon rho G. You know, this is rho and G is nothing but gamma. So you can write down gamma D square. Because this one V and one V will be cancelled, this will not be V square, it will be V only. So equation for the head loss for laminar flow, it is nothing but 32 mu LV upon gamma d square. This is the head loss for 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 laminar flow. Laminar. So why by using the Darcy Weisbach equation? Similarly, for turbulent flow, if you go for the second for turbulent flow, turbulent flow for turbulent flow, turbulent flow, and this for turbulent flow is as per the another scientist, that is his name is losses losses finding finding. Okay, it is given by the friction factor for turbulent flow is given by F is equal to 0.316 divided by R to the power of 1 by 4. And this is valid for this friction factor valid for values in between values of Reynolds number are in between 10 to the power of 4 to 10 to the power of 5. So that is more than 2000 Reynolds number, means it is nothing but the turbulent flow. And some scientists, they suggested that for all values of R, for turbulent flow in smooth pipe, not rough pipe, for smooth pipe, for turbulent flow, this R value is given by, it is given by epsilon upon delta dash should be less than equal to 0.25. And here you can say that epsilon is the average height of roughness, in the pipe, and delta dash the thickness of laminar sublayer. Thickness of laminar sublayer you studied in Moodys equation in unit number 3, and its value it is given by 11.6 nu upon u star. Okay, and nu is nothing but kinematic viscosity. Kinematic viscosity जो कि हम लोग फाइंड कर सकते हैं एक्सपेरिमेंट के जरिए. Viscosity. And u dash, u star is nothing but it is the shear velocity, and shear velocity is nothing but under root of tau 0 upon rho. यदि हम लोग ने देखा प्रीवियसली, और उसके लिए फ्रिक्शन फैक्टर 1 upon under root of f is equal to 2 log r under root of f minus 0.8, or in terms of fraction factor, if you write down 0.8, F is equal to 0.0032 plus 0.221 upon R to the power of 0.237. So this is the for all values of R, the frictional factor you can find out. Frictional factor you can find out. So this is all the for the frictional factor, and the frictional is nothing but the major loss in the pipe flow problem. Okay. Another scientist, that is Polo group equation for friction factor friction factor friction factor, that is F for smooth and rough pipe, for smooth and rough pipe, and it is given by 1 upon under root of F is equal to 1.14 minus 2 log E upon T plus 9.35 divided by R under root of F. Okay. So these are the different values of friction factor for the pipe flow problem. For the pipe flow problem. So we are used first the Darcy Weisbach equation, and from the head loss you can find out the friction factor, or you can, if knowing the friction factor, you can find out the head loss. Also for turbulent flow, by losses findings we have taken one value, that is F is equal to 0.316 divided by R to the power of 0.25 or R to the power of 1 by 4. And also this Colebrook equation to find out the friction factor, and based on this Colebrook, the Moodys diagram for commercial pipe is prepare the Moodys diagram. So Moodys diagram already I have made in notes, so I will go there to see the figures. So Moodys diagram based on the plot based on the Colebrook equation. So this Moodys diagram is based on Colebrook equation, and that you can see here. I will open that sheet. Colebrook wait. So this is here. You can see this diagram is visible, I think so. This diagram you can see here, this value in here. Here you can see it is 0, starting with 0.008, and this x-axis is for the Reynolds number. This is the, you can see here I have written, this is for the Reynolds number, and based on the Reynolds number, the friction factor you can find out from Moodys diagram, and based on the your flow. The y-axis, it is the friction factor, 0 to 0.1. Okay, this is the y-axis, and this zone is in between. I will write down this is the laminar zone. Laminar zone. The value you can see that it is from some 0.1 to some here. Okay, 0.01 something. Okay. Now here you can see I will draw with this transition line. This line, this zone up to this. This is the transition line. Transition flow आपको मालूम है. This transition zone as per the Reynolds number, and here I will draw a dotted line. So I will separate the transition zone with the turbulent zone. So here it is turbulent zone. Okay. So from this you can find out based on the E upon D value. This is the figure number 2, Moodys diagram. So from the Moodys diagram you can easily find out. From the Moodys diagram you can easily find out the friction factor based on your flow. And these are the lines. This is all this. Turbulent flow up to 10 raised to power 8, 10 raised to power 7, 10 raised to power 6, 10 raised to power 5, and 10 raised to power 4 is 10 raised to power 3. Okay, and also here the values 0.00001, this point 0.0001, 0.01, 0.02, 0.04, 0.05. This is the Moodys diagram. Okay, where you can find out the friction factor. You can see here. This is not. This is epsilon upon d. Sorry, epsilon upon delta or d. This is epsilon. This so will be this is the Moodys diagram. And turbulent flow. Based on that, you can get based on the Reynolds number. The flow is, we are defining turbulent transition. So like this is nothing but your Moodys diagram. Okay. So from the Moodys diagram, you can find out the friction factor by knowing the Reynolds number. Okay. So this is nothing but for today's lecture about the friction factor. So we are studying in this unit the flow through the pipe, and we have seen today before friction factor value, we have seen the Darcy Weisbach equation for loss of head in a pipe, and that we have derived the loss of head equation, that is HF 4F1 HF FLV square upon 2GD. Okay, and where F is the friction factor, and F dash is the friction coefficient, that is nothing but 1 by 4 of F. Okay, so this we have seen today in today's lecture. So I will share this sheet also, so you can come to know friction losses in the pipe flow. Some theory parts we have discussed, and then this derivation we have done, and we find out the head loss equation from the Darcy Weisbach equation. And here F is the friction factor, then different friction factor values by suggested by different scientists for laminar flow, for turbulent flow, we have seen, and also the Moody's diagram based on the Cole-Brook equation that also we have seen. So this is all about today's lecture, and tomorrow we will see the energy losses in the flight flow problem. If there is time, if I will get on Saturday, you have 3 lectures, just inform me. So tomorrow we will take another extra lecture so that your syllabus will be covered fastly. Thank you for joining, and in case of any doubt, you write for and with me. Lecture for today's we will stop here. Thank you for joining.